After we have studied the translational motion and fixed axis rotational motion of rigid bodies, now it's time to combine these two and study the general plane motion. The type of equations we're going to use are the same type of equation. We have one vector equation from Newton's law. It's the force equation, summation of forces, or the resultant forces acting on the rigid body. And the other equation is the moment equation, which we can write it with respect to the mass center, or we can use the alternative moment equation if we see it necessary. The same type of equations can be used. And again, this vector equation for Newton's law can be decomposed into two scalar equations depending on your selection of the axes. If you're going to select the rectangular coordinate system, then you can decompose it as summation of force in the x direction and summation of force in the y direction. As you remember, in the fixed axis rotation, we tend to use the nt coordinate system. In that case, we decompose this vector equation as summation of forces in the normal and tangential directions. The type of procedure is the same. We draw these free body diagrams to see all the forces acting on the rigid body. And there is this kinetic diagram, or the resultant force diagram, which shows these right-hand side of the equation, which could also be named as the D'Alembert forces anyways, but it's just the right-hand side of the equation where it includes the linear acceleration and the angular acceleration components. And if there are any constraints on the motion of this rigid body, then obviously we use these kinematic equations to get ourselves some extra information to solve our problem. A constraint could be a rolling motion, or it could be a mechanism. If we have this mechanism of a 4-bar mechanism, for example, and then there is this coupler link, the same type of examples always, I can recall. In that case, there is a motion of this coupler, which is a constraint motion, and it happens because of these links that are connected to the ground, or there could be the rolling action of a spherical object or a cylinder on a ground, and then the rotation and then the linear motion are related to each other kinematically. How that becomes a relation is due to the friction. If the friction is sufficient enough, then there's a direct kinematic relationship in between these two. We're going to take a look at an example based on this rolling action. Here we have an inclined surface. On the inclined surface, we have this wheel rotating, and the type of forces acting on this wheel at that instant, one of them is the gravitational force. Then there has to be a normal force applied by the surface to the wheel, otherwise the wheel will just fall down. So there are normal force, and in order for the wheel to rotate, there has to be friction force. If there's no friction force, then there's no rolling. It's just slipping. So there's that friction. But do we know the amount of friction? No, we don't know the amount of friction directly. We might know the friction coefficient μs, but that doesn't mean that we know the friction at that instant. Okay. We have already given a lot of examples on these in the previous lectures, so I'm not going to spend time on explaining again why the friction force is not directly equal to μs times n, because this is the maximum friction force that can exist at max friction force maximum. Okay. Now, in this example, we can use the frame in the direction of motion as x, and then the acceleration and the velocity of this wheel that is rolling will be in that x direction. And on the y direction, we do not expect any motion, because we are assuming that this wheel is on this slope, and then it's not losing contact and rolling on the slope. So we're not expecting any motion along this y-axis. Therefore, the acceleration of the mass center in the y-axis should be equal to 0. And if it rolls without slip, then we have this kinematic relationship between this rolling action and then the linear motion. And in the velocity domain, we can show that as velocity of the mass center is equal to r times omega. In the acceleration domain, this is the acceleration of the mass center in x direction is equal to r, which is the radius of this wheel, times the angular acceleration of the wheel, which is alpha. Now, how do we understand if there's sufficient friction so that the wheel will not slip? So no slippage will occur. How do we know that? We need to take a look at the maximum friction value, which is going to be calculated by this mu s, which is a static friction coefficient. Static friction coefficients term n. Do we know n? Actually, yes, we can find n by writing a scalar equation in the y-axis, and then the resultant of that will be equal to 0 because there is no motion in the y-axis. But the forces acting on the y-axis will be some component of mg, depending on its angle here. Let's call this angle theta at the moment. So that there will be mg cosine theta minus n. Well, let's put minus here because mg is in the negative direction. So let's be consistent with our selection. It's kind of impossible for me to put the minus, but let me put the minus here. So plus, and it doesn't really matter where you put the minus as long as you're consistent with what you write. So if there's a minus at mg cosine theta, there should be a plus in n because they are in the opposite directions. And from this equation, we can find this n, which is the normal force applied by the surface to the wheel. After that, we find out the maximum friction force. This is actually friction force maximum by multiplying this normal force with the static friction coefficient. And our expectation is if this friction force at that instant is less than this maximum force, then there's enough friction and the wheel will roll without slip. If it is more than that, then things change. We cannot write out this relation of A equals to R alpha directly. It will not be equal to R alpha. And then the friction force will be calculated by using the kinetic friction coefficient. So Ff will be determined in that case, and it will be determined as mu k times n. So we need to find out equations to check if this friction force at the instant of this motion is less than the maximum friction force. If it is less than that, no problem. Then there's no slip. The wheel rolls without slip. If it is more than that, the friction force required for the wheel to roll without slip is more than the maximum friction force, then slippage occurs and the friction force is calculated by using the kinetic friction coefficient.